A modern CPU can process billions of calculations a second, but it spends a surprising amount of that time sitting idle. It has to wait for data to travel from your much slower storage drive to the processor. This chart shows the massive speed gap between those two components. A CPU operates in nanoseconds, billions of a second, while a standard hard drive takes milliseconds to find your data. In computing terms, that is like waiting days for a single file to load. To bridge that gap, computers use RAM, or random access memory. If your hard drive is a massive filing cabinet in the corner of the room, RAM is the desk you sit at. By keeping your active applications and documents right in front of the processor, the CPU can read and write data immediately, without walking over to the filing cabinet every time it needs a new number. But building the perfect memory system is constrained by physics. Hardware engineers constantly balance a strict three-way trade-off between speed, manufacturing cost, and physical density. Because no single technology is perfect at all three, modern computers rely on a three-layered memory hierarchy to distribute the load. Understanding how these three layers, SRAM, DRAM, and virtual memory, interact is the first step to identifying if your hardware is actually the limit or if you're simply hitting a software bottleneck. The first layer is SRAM, or Static Random Access Memory. You will typically find this built directly into the processor itself as the CPU cache. This is the fastest memory in your machine. It operates in fractions of a nanosecond, allowing it to keep up with the processing cores perfectly. This diagram shows the circuitry making that speed possible. The single cell on the left takes a 6-transistor bistable latch to hold a single bit. Because of this design, it holds data securely with constant power. It never needs refreshing, earning the name static RAM. But storing a single bit takes up a lot of physical room on the silicon. When you scale that cell up to hold meaningful data, you get a massive, highly intricate electronic matrix. That complexity dictates the limits of the hardware. SRAM takes up far too much physical space and costs too much to manufacture to be used for your main system memory. While the cache handles the absolute most critical data right next to the processor, the system is forced to rely on a denser, cheaper alternative to hold everything else. That cheaper alternative is Layer 2, DRAM, or Dynamic Random Access Memory. This is the memory inside standard DDR4 or DDR5 RAM sticks you buy for a motherboard. To solve density, engineers stripped the memory cell to its minimum, just one transistor and one capacitor. But a capacitor acts like a leaky bucket, constantly draining its charge. Within milliseconds, a full bucket empties entirely, representing a zero. To prevent your data from vanishing, the system must supply a constant stream of power and periodically refresh the capacitor thousands of times every single second. All of that changing, reading, and refreshing action is why it is called dynamic RAM. Taking the time to perform those cycles also makes it noticeably slower than the static cache. However, cutting the design down to two components allows manufacturers to pack billions of them onto a single chip, driving the density up and keeping costs low. This makes DRAM the ideal candidate for main memory. It provides plenty of space at a reasonable price, but it still has a physical limit. If you open enough applications, you will exhaust your physical DRAM, triggering a software safety net. That safety net is Layer 3, virtual memory and paging. Without this layer, trying to load 20 gigabytes of applications into 16 gigabytes of physical RAM would immediately crash the system because there is simply nowhere to put the data. Your operating system manages this by sectioning physical RAM into frames. It packages inactive applications into pages and temporarily maps them down to your storage drive. This virtual illusion isolates programs, prevents fragmentation, and stops crashes when exceeding hardware limits. Warning tone. But there is a massive performance penalty. Hard drives and SSDs are exponentially slower than DRAM. A swap file forces the CPU to wait. The fast-flowing river of active data slams into the tiny drainage pipe of your storage drive. When your system is forced to constantly write to disk, you experience the stuttering and lag common in older machines. Your perceived speed is effectively capped by how often you can avoid hitting this safety net. How do the physical limits of these three memory layers translate to your wallet? It depends entirely on how often your system is hitting that safety net. This chart maps your daily software habits to your required capacity. Let's walk through the three paths. Path B is for computers running fine. If your workflow fits comfortably inside your physical DRAM, buying more RAM yields zero return on investment. Think of the desk analogy. Once your desk holds your active papers, making it wider doesn't help. Path A is different. If you run intensive workloads with insufficient DRAM, the system is forced into virtual memory swapping. Upgrading RAM here is mandatory. Expanding physical capacity eliminates performance drops from the hard drive bottleneck. Path C applies when buying new. Casual buyers should aim for 8 to 16 gigabytes to avoid the paging penalty. Power users should target 32 gigabytes or more. Whatever capacity you choose, install the RAM sticks in pairs to utilize dual-channel memory, doubling data bandwidth to the CPU. Do not overspend on excessive capacity you will never touch. Reallocate that wasted budget toward a faster CPU or a better graphics card. The goal of an upgrade is to provide enough physical DRAM so your active programs never page to disk. This keeps your data flow contained within the hardware's fastest circuits, allowing your processor to rely on its lightning-fast SRAM.